All right, we finally have reached the point where we're going to do our first QFT scattering calculation. That's the purpose of this lecture. As a little bit of a recap, recall our overall experimental setup. We basically have some sort of thing which you can call a particle collision chamber, and at an initial time, which we usually call T naught, we are introducing, for example, two particles, one of known momentum P1 and the other one of known momentum P2. This quantum mechanically will be an eigenstate of our system. Then all of a sudden, these particles undergo some sort of interaction. Remember, with their interaction Hamiltonian, that changes the eigenstate of the original Hamiltonian to now some new state. So this whole state evolves because we are changing our Hamiltonian from H naught to H naught plus H sub I. And then at the end of our experiment, after a certain amount of time, which when we look at everything at a time TF, then we have a situation where we look at our collision chamber and we have these detectors that can detect different things. And you may have a situation where these detectors detect, for example, three particles, one of momentum P4, the other one of momentum P5, and the other one of momentum P6. And then sometimes we'll just say momentum, but I really mean momentum and energy, P4. These are four vectors. And the detector may detect something like this. In this lecture and for these calculations, we're just going to focus on 2 to 2 scattering, meaning we start with two particles and we want to calculate the probability that we're going to still see two particles at the end. The final state may be a mix of particles, as we've talked about in the previous lectures, but we are specifically going to calculate only those situations where we will see two particles. In this case, we start with particle P1 and P2, and then at the end of the experiment, we still see two particles with our detectors, but we measure Q1 and Q2 for momentum and energy. Or you start with the same situation and you may measure two particles, but at different momentum, Q1 and Q2. Or you start with two particles, and at the end of the experiment, you still just see the same original two particles and same original two momentums, P1 and P2. That would be called no scattering. That's our basic overall experimental setup. And now our goal, which is pretty exciting, is to calculate how often we will observe these various outcomes. Experimentally, we see that if we introduce two particles like this, and then we create the same experiment thousands or millions of times without changing any of the initial conditions, we will see, according to quantum mechanics, that even though the experiment is identical, that we'll get different outcomes. We really want to calculate what are the different probabilities of getting these different outcomes. Here's our mathematics and our theory that we've developed pretty extensively over the last many lectures. Remember, we start with an original Hamiltonian, which we can express this way as omega p, a dagger p, a sub p. This is the Hamiltonian expressed in this a dagger formulation. And we sum over all potential p's, all potential momentums. Remember, when a p has an arrow on it, that's supposed to be a three-dimensional vector. And when it doesn't have an arrow on it, it's supposed to be a four-dimensional vector. That was the Hamiltonian that we did originally. And then when we start getting the particles together, we assume, as we've talked about before, that we get an interaction component to our Hamiltonian. So we do H naught plus H sub I. And for our purposes here, for this scalar 5/4 theory, which is somewhat of a toy theory, but very instructive at teaching us all the essential ingredients of quantum field theory, we assumed that Hi is the so-called 5/4 theory, where you take this phi and you raise it to the fourth power. That's technically the Hamiltonian density at each point in space. And then we integrate that over each point in space. And then we have this prefactor of this coefficient, which tells us the strength of the interaction, called lambda, divided by this funny factor of 4 factorial. In this lecture, you'll see why we kind of arbitrarily added that to our toy theory. It makes things easier mathematically later on. And remember phi, which is over here. We spent a lot of time redeveloping the interaction picture of quantum mechanics. That's what allows us to really solve problems in QFT. Our phi expressed in the interaction picture is going to be this. Phi of x is equal to these prefactor constants, a sub p e to the minus ipx plus a dagger p e to the plus ipx. And the key thing is this p and this p are 4 dimensions, and so is the x and this x. So this is a function ultimately of space and time. This x is 4 dimensions, this x is 4 dimensions, this x is 4 dimensions. And this p, which p times x means the 4 vector p, dotted with the 4-vector x. We went over this before. But this is the formula we're going to use for phi that we're ultimately going to plug in here. We start with the very specific initial configuration. Here we're going to just focus on the case of starting with 2 particles, and we also want to see the chances of ending with 2 particles of potentially different momentum. We say we can write it in different ways, but we can say it like this: one particle of momentum P1, another particle of momentum P2. Remember, when I say momentum, it really means momentum energy P1 and momentum energy P2. Our interaction, H0 plus Hi, starts at the time T sub I and continues until the time T sub F. In QFT / particle collisions, we assume that this time of interaction, in other words, the difference between TF and T sub I, is essentially infinite. If we wanted to break it down a little bit more clearly, we sometimes call infinity this dimension capital T, which is really the length of our box. So if we think of space of our interactions, our whole theory taking place in a cubical huge box of length L on each side, then we also think that the time evolution for our interaction is of the same dimension. Remember, space and time in special relativity can be made in the same dimensions and treated essentially with equal footing. So we basically say we have like a 4-dimensional cube of each side being L, 3 spatial dimensions and 1 time dimension. And then sometimes instead of using the word L there, we'll use the word T. But basically, we approximate that as a huge amount of time and a huge box, which is essentially infinity. In the prior lecture, we learned that there's an operator, U, T sub F minus T sub I, that tells us how the initial QFT state, which I could just call this, like psi with the sub I for the initial state. In this case, that initial state was P1, P2. This is the ket that we use for our initial state. How our initial state changes under H sub I to a new final state psi sub F at TF. And we learned in our previous thing that U, this operator that will magically kind of take you from your initial state to your final state if you just plug in what the time difference is, that U is given by Dyson's equation. That's what we explained in the last equation, in the last lecture. And this is Dyson's equation over here. U of T sub F comma T sub I is equal to U. And then T sub F and T sub I, you can just assume they're plus infinity, minus infinity, or something similar to that. Remember, infinities are something we use somewhat liberally back and forth here. And then that Dyson's equation says that this operator is this, that we take E, the exponential function, minus I integral of from Ti to Tf of this interaction Hamiltonian, H sub I, evaluated at T prime, dt prime. This is the formula we came up with before. And the only thing I just didn't mention right now, which I mentioned before, is that we have to use this T. And this T here, sorry, is different than this T here. This is the time ordering operator. It says that we take this entire expression, and anytime there's a product of operators that are evaluated at different times, we have to take their time ordering, meaning that we put the earlier time to the right and the later time to the left of the operators, as we explained before. This is Dyson's equation. For 5-4 theory, we simply plug in our H sub I here, and that's what we get over here. Remember, H sub I is evaluated at a specific time, and our Hamiltonian density is this, which we integrated over space, and that's why we get this. We have an integral over time coming from Dyson's equation, from time equals negative infinity to positive infinity, or, you know, this big T could be replaced with this infinity difference. And then we also have to integrate over space because this is the spatial density from all of our boxes of our cube. So we get this really effectively, ultimately 4-dimensional integral because we have a dt and then a dx. There should be a little dt here as well. And remember what this exponential stands for. It's this over here that we first take 1 plus this factor itself over here, plus this factor itself squared over 2 factorial, and then the product of the two. This is what the exponential stands for. And here, when we use this single integral d4x, what that really stands for is 4-dimensional integral over essentially infinity, or all the dimensions of our space-time box where our interaction takes place. So this is U over here. We're now going to apply U term by term to our initial state to determine our final state, and really look at this final calculation for scattering. As before, we mentioned that lambda is this fraction between 0 and 1. And because of that, and each of these terms will get progressively smaller than the previous term, because this has no lambda to the 0th power. This has lambda, which is a fraction to the first power. This has lambda, which is a fraction to the squared. Remember, if you square a fraction, it gets smaller. So progressively, each of these terms will be smaller than the previous term. It's when we do Dyson's equation, we can't really solve anything exactly in QFT with interactions. So we're going to use what's called a perturbation approach, and that's what this formulation allows us to really nicely work with and calculate. We're going to approximate our final answer, which is the final state of our system after the interaction takes place, psi sub f, by just picking more and more terms. We obviously can't pick an infinite number of terms, but the nice thing about this perturbation setup is that each term in this U operator is getting smaller and smaller. So presumably, if we just include this term, that's the biggest contribution to our answer. That gives a pretty good answer, but not perfect. If we add this term to this term, we just use two terms, we get an even better answer. And then if we add three terms, we get an even better answer, so on and so forth. So just by adding more and more terms, we get more and more accurate answers. After we use U to get psi final, there are two ways of doing business. This is just from quantum mechanics. We can write our entire state, psi final, as just a combination of all of the basis states. We have a ket in our QFT space, and that can just be obviously expressed as a sum of basis vectors over here. And remember, the basis vectors themselves can be various choices, but a really good one that is very physically clear is to use the basis vectors of our Fock states. And these are states of specific momentum, P1, P2, or P3, P4, so on and so forth. And included here will be states that also have multiple particles, no particles, various scattering amplitudes that give us a complete Fock state. And we can kind of use this U to crank it out and completely express our final Fock state like this. And then if we did that, we can read off the alpha sub i's to look for the specific transition we're interested in. The word transition is used a lot just to say we start an initial state and it transitions to a final state. So we will sometimes use the word transition or transition amplitude. And basically, if we wanted to figure out what's the chances of starting off in this state and then ending up in measuring that we end up in this state, we don't actually end up in this state mathematically, but we do a measurement and see what's the chance that a detector will show us this final state. Just from quantum mechanics, we can just find the basis vector associated with this, which is over here. Look at its, in this final expansion, look at its coefficient, which is in general a complex number. We take the modulus squared, and just from basic quantum mechanics, we know that that's the probability in this. If this is our final state, this is if the probability of our detector measuring this, which represents two particles, one of P3, one of P4, will just be this coefficient modulus squared. That's the probability of starting with P1, P2 and yielding P3, P4. That's kind of one way of doing business, just writing out this entire final state. The other one, of course, is that we can just do it this way, that if we want to get our answer directly, we can just take our final state here, convert it from a ket to a bra, like this, and just take the inner product of that with the final state. So you're taking the inner product of this with this entire expansion, apply it linearly to each term, and then we get something like this. This applied to this, this. This is the technically, remember our final state here, I got from using the U operator applied to our initial state. That's what the Dyson's equation tells us, and that's what this is expressed over here. So that inner product becomes expressed like this. And then why does this work? Well, it's just the same as any other reason in quantum mechanics. This Fock state here expressed as a bra rather than a ket is orthogonal to every other Fock state in this expansion, and it's normalized to 1. So we should get the same thing if we take this thing and apply it to every term in this expansion with an inner product. Every other term that's not exactly this will equal 0 and drop out. And then when we take the inner product of this with this specific term that's identical to this, that's normalized to 1. And then we just pick out alpha 2, because that inner product becomes 1. And then that alpha 2 is the so-called transition amplitude that we're interested in. That's the word that people use. And if we take the modulus of that squared, then we get our probability. That's the other way of doing business. When we do QFT, we're really going to use this second approach when we do our calculations. It doesn't matter a lot, but I'm just trying to be explicit here. But rather than write down the whole thing and then take the inner product to get our answer or read it or read the coefficient, we're going to actually take the inner product right from the beginning of this with this, which ends up being some expression like this, and that'll give us our final transition amplitude. And the word that's generally used in most books is SF sub I, S as being the transition amplitude or the scattering amplitude, and F means the final state, I means the initial state. And then if you take the complex modulus of this SF sub I squared, then you're going to get your actual probability of measuring that interaction. This is somewhat annoying but important. I like various textbooks. This entire lecture series is based on a lot of different textbooks, some of my own ideas as well that I've learned over the years from studying different things. We haven't talked that much about special relativity. We did in I think the second lecture or third lecture. But in order to be consistent with something called normalization or relativistic normalization, we need to kind of do a certain slight adjustment to what you would think our initial states would be. You can see David Tong's QFT lectures for a little bit more justification on this. But basically, this is what we're going to do throughout this lecture series, just to be consistent with that, which isn't, it's a little bit annoying, but it's not a huge adjustment. In our particle collision chamber, when we experimentally see, for example, one particle of momentum energy P1, we use the word here mom energy, but P1 is a 4 vector, so the first component is energy and the other 3 are spatial momentum. If we see one particle of momentum P1 and another particle of momentum energy P2, for instance, this may be, for example, this may be what we initially introduced into our chamber. We postulate that this state of known momentum energy P1 and another one of momentum energy P2 is not just this, which we've talked about in great depth, where you take the vacuum state and you dagger it. You'd use this creation operator, A dagger sub P2 acting on 0, and then A dagger sub P1 acting on that same thing again. That does give us a 2-particle state, but to be consistent with relativistic normalization, remember for any state in quantum mechanics, that is even quantum field theory, you can always adjust the, you can always multiply the state by a constant, and that vector essentially becomes a ray, and they all represent physically the same state. So we have we have the freedom to add a prefactor here, and it turns out to be consistent with the theory of special relativity, which is what our whole theory is based on in a deep way. We have to use a relativistically normalized state every time we do this. So what we introduce in the lab as our 2-particle state of momentum P1, P2, we still use the same situation. We A dagger it, the vacuum state, but then we just use this constant factor that we pre-multiply it by. And this is the prefactor, the square root of 2 omega p sub 1, square root of 2 omega p sub 2. The energy, omega is the energy of the particle that has spatial momentum P1, and omega p sub 2 is the energy, omega is the energy of the particle that has spatial momentum p sub 2. And this is what we're going to do. So technically, when we're introducing our particle into the system, our 2-particle state, this is what we want to do. Not just this, but we have these prefactors here that we multiply it. And similarly, at the end of experiment, when we say our detector shows us a final result emitted from the collision of, say, one particle of momentum energy Q1 and another particle of momentum energy Q2, we postulate that we're detecting the relativistically normalized state, not just A dagger 0, but same thing. Our final state is Q1, Q2, but we multiply by this prefactor 1 for each particle, square root of 2 omega Q sub 1, square root of 2 omega Q sub 2. So this is what we do in our calculations. You can look at David Tong for a little bit more justification of why that's consistent and needed for the theory of special relativity. All right, so in this lecture, we're actually only going to calculate the first and second terms of this whole expansion. We can theoretically calculate an infinite number of terms. We're going to leave this term for the next lecture because it has this factor of t, which is the time-ordered product of this, and that we have this is tricky to deal with mathematically, and there's a wonderful theorem called Wick's theorem, which is very important in QFT, that will help us deal with this time ordering and change it to something that we can deal with more easily. So for this lecture, we're going to ignore this part right now and really just get our zeroth order calculation and our first order calculation, which is pretty accurate, not perfect. But remember, the more terms we include, the more accurate our calculation becomes. And as we just talked about a lot, we're going to specifically ask the following experimental question. If we start by introducing into our interaction chamber one scalar particle of momentum P1 and another momentum P2, what are the chances after the interaction is complete of finding two scalar particles of momentum Q1 and Q2? These are finals, these are initials, and 2 to 2 scattering. Our initial state is this that we're starting with. Our mathematical representation of our initial physical state is this, psi initial, and that's taking the vacuum state, daggering it with a dagger piece of 1, a dagger piece of 2, and then adding this factor for relativistic normalization like we just talked about previously. The notation here is interesting, and I'll go over this a couple of times. When we write P1, P2 as this ket, and we don't have an arrow over it, this is somewhat confusing, but also simplifies a lot of nonsense sometimes. When we don't have an arrow over this, we mean a two-particle state that is relativistically normalized, like this. Turns out when we do have an arrow, and I'll show that in the next couple of slides, that means that we're not using this prefactor. We just have our two-particle state, but not relativistically normalized. I'll show you that some more. But this is our initial state. We're going to time evolve this with this operator u, according to Dyson's equation, and then we're going to project this onto the following state to get our transition amplitude. Our final state is two particles in this particular situation. That's what we're interested in looking at, and we call their momentums Q1 and Q2. This is the ket. The bra, obviously, with this is we just flip this over, Q1, Q2, and this is how we write our actual final state. We do missed a little bit here, so just going to just do this for a second. Here's our actual final state over here. We basically take this same thing here, and then we just take its conjugate, and that's how we convert the bra to a ket, which is 0 here, the vacuum ket. And then we have these same factors. They don't change when we change from bra to ket, take the conjugate. Square root of 2 omega q sub 1, square root of 2 omega q sub 2. And the daggers just become the non-daggers. Remember, the Hermitian conjugate of this is just the non-dagger things. So this is our final state expressed in this kind of bra form over here, a sub q1, a sub q2. So that's how we express that there. Just some basic terminology here. Remember, this u operator we're going to express as this huge sum of terms that these all come from the exponential, as we've talked about. And the first term here is called the zeroth order term, which we're going to calculate in this lecture. And this next term over here, we call it the first order term, S superscript 1. And this term we call the second order term, S superscript 2, so on and so forth. And what these orders refer to are 0, 1, and 2 are the orders of lambda. Lambda here is not included, so technically that's lambda to the 0 or 1. Lambda here is included, but just to the first power, so that's why I call it the first order term, S superscript 1. And lambda here will be squared, that's why it's called the second order term, so on and so forth. That's just some basic terminology. All right, so first thing is some preliminaries, a little bit of annoying mathematical details, but actually very important to help us in the next few slides to understand our calculations. Now, we started mentioning this before, but this is how we use our notation. We've talked about this once before, but recall when we write this over here, this is a ket that represents P1 and P2, two particles, one of momentum energy P1 and the other momentum energy P2. When we don't put an arrow on top of this, this represents the following, that we basically have a state of two particles, which we can create by acting on the vacuum state with a dagger P1, a dagger P2. This is the part I sometimes forget over the a daggers, but at least the way we write things here, the a dagger, when I write P1 and P2, it doesn't really matter if it has an arrow or not, but it's technically supposed to have an arrow. Um, when I do that, I get a state of two particles, but it's not relativistically normalized. So when I just write P1, P2 with no arrow on it, it also implies that I have this extra factor for relativistic normalization that we talked about before, the square root of 2 omega P1, the square root of 2 omega P2. So that's just notation. This thing itself, when I I can write it like this with, and this is a P1 P2 ket with the arrow on top of it. So when I have the arrow on top of it, it refers to just this over here, a two particle state that's not relativistically normalized. But when I write the same thing without the arrow, by definition, I have the relativistic normalization factors here. That's just one kind of bookkeeping thing to keep in mind and notation. Um, Remember also that our old formula here, that in at least in the discrete form, we have the commutator of AP with a dagger Q sub Q, and that is equal to delta PQ. This is the Kronecker delta. And if you just expand this out for what the commutator means and then just shift a term, this is the equivalent over here, that you have this equivalent formula. Similarly, I can do this same type of exercise with the bra. Here I have the bra written, Q1, Q2, and that's this over here. I just change everything to the vacuum ket to the vacuum bra, and then A sub Q, A sub Q2. The daggers become non-daggers because you take the conjugate of this whole thing to get that just from standard quantum mechanics. In this case, I don't have the relativistic normalization factors, so I just have an arrow over the Q1 and Q2 as per our convention. Now, we calculate this important quantity, which will be helpful in a little bit. If I want to take the inner product of Q1, Q2 with P1, P2, I can just crank out our formula here and see what we get. And it's somewhat easy and for the most part somewhat obvious, but you have to keep track of some of these factors sometimes. So this is this factor over here. So I'm just expanding this out over here. This over here, this bra is equal to this over here by definition. That's just what this is. And this here with the arrows on top of it is equal to this by definition. Because they have arrows, I didn't include the relativistic normalization factors. I can manipulate this expression in different ways, but the most reliable way, which is a little bit tedious, is just to use our commutator formula here. And if I do that, I can change these two factors by using this commutator law and get this over here. So I still have this 0 here, a Q1 here. And this thing here, you can just use this formula here based on the commutator formula. I can reverse this and put the dagger here, and put this a over there. And if I do that, I have to add this delta function, which is based on the commutator. If I commute these two, because they don't perfectly commute, P1, Q2, this over here stays the same as there over here. And then if I just expand this out, this is what I get here, 0 from here, a sub Q1 from here, a dagger P1 over here, a Q2 over here, and then just this factor here, I distribute this out, a dagger P2 with 0. And I do the same thing to get this over here, this, and this, and this, to give me this. And this is what I get there. This delta function is just a number, so it could be pulled out of this whole inner product out in the front. And then I get 0, and just what's remaining, a sub q, a dagger p sub 2 of 0. And then I can apply this commutator formula again to this expression, and I get this original prefactor, which doesn't change. And this thing, I change the a and the a daggers, so that the a dagger is here, and I'm just keep pushing the a non-daggered all the way to the right. That's what's going to end up killing things and making the calculation easy. So I push this over to there, but because these don't commute, I have to add this factor per this formula of the delta of the Kronecker delta function. So I get this over here, and again I distribute this out. This here, this here goes here. This factor over here comes over here. I just use the second term, made it first, and then I still have 0 with 0, and that inner product always evaluates to 1. The vacuum state is normalized. And then I do the same thing with the other part over here. I have this delta function over here. This 0 goes over here. This a dagger P2, a sub Q1 is over here, and 0 over here. Now here's an important part. A sub Q1 acting on the vacuum state gives me the number 0, the mathematical number 0. We've talked about that a lot. There's nothing below the vacuum state, and this is a lowering or a destruction operator. And when there's when you're acting on the vacuum state, you just get the number 0, and that makes this whole expression 0, which basically makes this whole expression equal to just this delta function, since this is 1. So that's how I basically rewrote this thing here as just this is the final answer for that. And now for this expression here, I still continue to do this game where I take the a's and I try to keep pushing the a all the way next to the 0. And that's how I did this here. I just keep writing this here, this a sub q here, this a dagger p1 here is still there. These two I changed the terms, so I put a parentheses and I put the dagger first and this thing over here because they don't commute. I have to use this commutative formula, and that the correct expression is this over here where I have this Kronecker delta function applied here again. And then I play the same game that I'm going to expand this out. This a sub q is going to be right next to this vacuum state 0, so that's going to kill this term. Whatever this ends up being, this is going to kill this. A sub q next to this is going to be equal to 0, so this part of this will get canceled out, and all I'm left with is this expression, and this delta will be pulled out in front like we did just before. And then I have 0, a sub q1, a dagger p1 acting on 0. That's this here, and then this term I just completely copied down below. It doesn't change. That's the expression I get here. I'm going to do the same game again where I'm going to commute these so that I have the non-daggered a right next to the vacuum state 0. And then I have to use that same commutative formula. The a, when I switch this around right next to 0, will get killed. But when I commute this, I still will have that delta q1, p1 over here. And here's my delta p2, q2 that's still over there. And then the 0, 0 will be normalized just like this. You can play around with these formulas just a little bit. It's somewhat obvious and tedious, but you should still do it because it's good exercise to play around with these commuters and these commutator laws just to keep track of the algebra. And this thing is still unchanged over here. So in other words, this entire thing where I take the inner product of a two-particle state, non-relativistically normalized because I have the arrows on it, with another two-particle state, non-relativistically normalized, which is why I have the arrows over it, will give me this expression over here. And what it states is what you may kind of intuitively know from earlier lectures here, is basically that if I have a two-particle state, which is technically a Fock state, and I take the inner product with another two-particle state, Q1, Q2 with P1, P2, I'll get 1 if these two things are identical, which you could say that means Q1 equals P1 and Q2 equals P2. Or, of course, because it doesn't matter which particle we're talking about, the thing's essentially indistinguishable. Or if Q1 equals P2 and Q2 equals P1, which I just kind of abbreviated like this, if those are the same, then I just get the number 1. That's what that previous delta stuff will factor out to. And if these are not identical, I just get 0. And it's kind of intuitive what you expected, but this is just the proof for what I just showed. So now that's for this. The expression that will come up in these next slides very shortly is, what about the inner product of two states that are relativistically normalized? Do I get exactly the same thing? Well, we can just write things out and see and have it figured out once and for all. Well, remember this thing over here, non-relativistically normalized, is just this. This one relativistically normalized is this non-relativistically normalized Q1, Q2 with the arrow. And then I add the factors here of square root of 2 omega Q1, square root of 2 omega Q2. This whole expression over here is this expression over here. This is relativistically normalized by taking the non-relativistic normalized, multiplying with these appropriate factors. And I do the same thing with P1, P2. I have the arrows plus the relativistic normalization factors to give me this. And then these are just factors that you can pull out of the inner product. Of course, pull this all in the front. And then you just have this inner product, which we just spent calculating, and the answer is right up here. And then these factors, you have square root of 2 times square root of 2 times square root of 2 times square root of 2. That just gives you 2 times 2, which is 4. And the square root of all of this stuff can be put under one big square root. And then this thing here, we've already calculated here, so we just have this factor that multiplies by 1. So this is our final answer for this. The inner product of these two is not quite just 1 or 0. At least for these relativistically normalized states, I get 4 omega P1, omega P2. If these two states are identical, otherwise I get 0. And identical means I could do this equals this, or this equals this, and then this equals this, or this equals that. How do I get this? Well, if these two states are identical, then the Q1 and the P1, for example, will be the same. So I can just call that P1, and then you have the square root of P1 times the square root of P1, which just gives you non-square root omega of P1. And same thing with the P2. And it will work out the same if Q1 is equal to P2 and Q2 is equal to P1. So that's where this comes from. So just a handy formula to have for our future calculations for relativistically normalized Fock states and for relativistically non-normalized Fock states over here. And the general form, which we'll just use this expression later, is this. This is, you don't have to write it like this. This was the generalized delta function that we used from the just on the previous slide. Okay, so now having gotten that preliminary stuff out of the way, let's go ahead and do our first calculation and look at the zeroth order term of our transition amplitude. Just to show again what we're doing, here's our entire expansion, our Dyson expansion. The zeroth order term is just this term, which is just 1, or the identity. Remember, these are all operators. This is the identity operator. So using our way of figuring out transition amplitudes, we have a two particle scattering, meaning we start with two particles, one of momentum pi and the other one momentum p2, p1 and the other one of momentum p2. And then we want to see what are the chances to zeroth order of identifying two particles at the end, but one of momentum q1 and the other of momentum q2. And all we do is plug this in right in the middle, because this acting on this will give us our final state, remember? And to the zeroth order, the U operator acting on our initial state will take us our final state, and we can just take the inner product of that with the final state we're actually interested in to see what are the chances of getting this transition amplitude. So the identity operator means we change nothing, so we just get this simple expression here. Remember, both of these are in relativistically normalized formulation, so that this is not just equal to 1 or 0, but as we just showed on the previous preliminary calculations, this. So this whole thing is equal to this, as we talked about before. So this is equal to 0 if these two states are not identical, and this is equal to this 1 times this, which is really 4 times omega p1, the energy of p1, and then the energy times the energy of p2, if these two states are identical. And that could either be that q1 equals p1 and q2 equals p2, or the other way around, q1 equals p2 and q2 equals p1. So that's our answer for our first transition amplitude. What does that mean physically? Well, pretty simple to interpret, but also important to see that our theory actually produces something reasonable. If our two states are identical, then we get this, and otherwise we get that, repeated from before. So according to our calculation, the physical interpretation, to zeroth order, when we place two phi particles of momentum p1 and p2 into our collision chamber, and then see what happens after they're allowed to quote unquote interact, the chances of us observing any change in momentum or energy of the two exiting particles is 0. So the two particles we put in, and basically nothing happens to zeroth order. Always we'll see the same thing coming back. Our chances of measuring that the two particles will be the same is this. Remember, these are transition amplitudes. So in quantum mechanics, you have to take the complex modulus and square it. For this number that's not complex, we just take 4 omega p1, omega p2, and the whole quantity we square. And that's what we get here. So technically, probabilities are supposed to be between the range 0 and 1. So we have a little bit of a problem here. Our probability is more than 1, potentially. 4 times the energy of P1 times the energy of P2, the whole quantity squared. That's not really a problem. We just realize that when we do these calculations, our actual probabilities are technically the ratios of different possibilities. So the chances of measuring exactly the same thing divided by the chance of measuring anything different is what is the factor that counts. So that's what means anything physically. So that's fine. We're just looking at our calculation as if it's telling us it's more likely to get this than that, and infinitely more likely here because the other chances are 0. If you want to continue to have probabilities themselves between 0 and 1, we could just normalize these, basically meaning divide everything by, in this case, this 4 omega p1, omega p2, and then it'll normalize it so that we can actually get a probability of starting p1, p2 and just ending with p1, p2 is just 1 after we do that normalization. And still the chances of starting at p1 and getting q1, q2 for anything different is 0. So to zeroth order, there's no interaction a 100% chance that whatever we put in, we'll get right back, even after the interaction is turned up. It's a zeroth order. So that makes sense, maybe for zeroth order. Now we want to see something different because we know based on physical experiments, sometimes we put two particles in and they quote unquote collide and we'll get two different particles, or two particles at least with different momentum and energy sometimes. So let's now look at our first order term. That's going to help give us the physical finding that I just mentioned. So the first order term is this. So in order to figure out the first order, eventually we're going to have to add the two, but I just want to hit this part right now and calculate this term right now, the second term, or the so-called first order term here. So what I do, remember, is we start with our initial state here, and we're going to just use this part of u and hit it with this, and then take the inner product of that with our desired final state to give us a chance of actually seeing Q1, Q2. So this is the actual thing that we have to calculate right now. Before we do this calculation actually gets somewhat tedious, and a lot of QFT calculations get very tedious. And we want to be right in our calculations, but at the same time, we don't want to lose sight of the forest for the trees. So I'm going to sometimes simplify things by pulling out and ignoring constants, at least at first, so that you get a rough idea of the calculation. And inherently, it's actually pretty simple and very fun once you actually once you understand how things work. It's kind of an enjoyable mathematical calculation if you go through it step by step. Math in general is a big turnoff for a lot of people learning physics, and the higher level physics, the more math it is, but don't let it be a turnoff. It's just basically simple steps, step by step by step. If you stand back and look at the whole calculation and say, wow, I don't want to have anything to do with this, but if you start going through things one by one, it all makes sense, and it has to make sense. It can't be any more complicated than stuff that you do in day-to-day life. It's just symbolism for things. All right, so let's look at this calculation, big picture, and then we'll get to the details in a little bit too. So here's our thing that we're trying to calculate. And before we do this, we actually just take this phi and use our classic expansion. I called it our old friend, the thing that I asked you before to memorize. But remember, the phi expansion is this in terms of a and a daggers. There's these factors of e to the ikx on both sides, minus and plus. And then this is technically not what we started with in terms of our Schrodinger picture, but this is all now expressed in the interaction picture as we explained in great depth. So this is technically time dependent. This x stands for time, and then the three spatial numbers. So it's a 4-vector. This k and this x are also 4 vectors, and same thing with this k and this x. These p's and this sum over k's is technically over just 3-dimensional momentum vectors. But here's our expansion, which we're going to take this and just plug it into this and see what we get. We're going to have to do this 4 times because it's phi to the 4th power. So we'll do this phi times phi times phi times phi. So we're going to take this expression basically and multiply it by itself 4 times. This is a dummy index, so we're just going to change this k to ki, and we'll do k1, k2, k3, and k4, just since each of these expansions are independent. And one thing I'll say is technically, this is what we're trying to calculate. These things, again, are relativistically normalized, so they have those factors of square root of 2, omega p1, etc. And same with this. But at least the intuitive part of the calculation is easier if this is not expressed like this, but expressed in terms of just the 3 non-relativistically normalized thing, which has the arrow on top of it. Because, for example, if I do this, which is a destruction operator on this 2-particle state, you remember from our earlier lectures, if I take a k sub I and act on this, if this k sub I is not p1 or p2, this whole thing just equals 0 because it just collapses to 0. If this k sub I is like p1, then it's going to just knock out p1. It's going to get rid of my 1-particle state and just give me p2, which it's going to get rid of my 2-particle state and just give me a 1-particle state p2. And then if this ki happens to equal this one, it's going to knock out this guy and turn my 2-particle state just to a simple 1-particle state. So that's a nice little mathematical formalism. We don't have to worry about extra constants if we just are dealing with these non-relativistically normalized factors. We can change this to this via just adding our formula for the square root of 2. But it's a little bit more direct with this, sometimes more intuitive than hitting the a without the dagger on this, which will be similar to this, but then you have these other constants you have to worry about. And this is our way to convert this into this, the non-relativistically normalized one, and then we can pull these factors out later and just deal with the A's and A daggers. So here I kind of, on this next line, we'll pull out a bunch of stuff from this inner product. I'll pull out this factor over here, minus I lambda over 4 factorial. We'll just pull that out of the inner product. This integral over d fourth x I can also pull out of there and put over here. A lot of these, these sums that are going to be here, I'm going to also pull that out of the inner product. I'm going to have 4 different sums. I just symbolize it here as a single sigma sign, but wrote ki for k1, k2, k3, and k4. It's really 4 sums over here. I could pull out some of these other factors as well, like these radical 2 omega p1s. I didn't show it here. I just put a proportional sign just to show that these things can all be pulled out of this inner product. And then I just look at this inner product once I take all that other stuff out of it. And that's what I have here. I have these non-relativistically normalized things. And then 4 times I have this phi expression once here, once here, once here, and once here. And I called the first one K1, K2, K3, and K4. And each of these are ultimately going to be summed over Ki. So take a moment and make sure you understand that. I told you also I still omitted some more factors that would be here outside of the inner product, like these types of factors for clarity, for the big picture part of our calculation first. Let's continue to look at this. And just for a moment, let's also forget about these e to the ikx factors and just look at the a parts and the a dagger parts. Sorry. So recall from basic high school algebra that I basically have a binomial term here times another binomial term times another binomial term times another binomial term. And we know how to expand this. So normally from high school algebra or even less algebra, 7th or 8th grade algebra, you're just basically going to get a massive expansion of each term. You pick the first term, 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 second term, so on and so forth. And you can get things like this. These were just regular numbers. We do the same thing here, but they're operators, but the same idea. So we can pick out this guy over here, this guy over here, this guy over here, this guy over here, and I'll get something like this. I'm ignoring those e to the ikx factors, and that's this one over here. I still have the inner product q1, q2 with p1, p2, and between the two, I'll have a sum of all of these different terms. So I could break it up into this, plus this, plus this, plus this, plus this, and so on and so forth. But at least I wrote down the first one here is where I just picked the first term out of each of these. These are the A non-daggers, AK1, AK2, AK3, AK4. And then same thing here, I just picked out this A dagger from this first binomial term, and then I just picked out the A's, and that's this thing here. These are all ultimately going to be added together. Here I did the same thing, except I picked out the second A dagger and just left the first and the other ones with just the A's. And you can imagine every combination over here. I'll get 2 to the 4th, I think, terms here total. I just put dot, 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 so I don't have to write all of them down. And I just kind of highlighted 5 of them over here, which we'll look at now in the next few slides. We can calculate each of these guys individually. Ultimately, our answer should be these all added together. So let's look now at the first term. We're going to calculate this over here, which is part of our overall expansion. And again, we are ignoring some of these e to the ik factors just for the big picture I want you to understand. So let's calculate this over here. That we want to calculate this whole thing here, and I kept this sum over ki's. Technically, there's a sum over the k1, k2, k3, and k4. Let's see what happens. Well, the first thing is I'm going to take this thing, which is all the way to the right, and operate on this ket, a k4, and operate on this. And I'm going to really take a sum over k4. So this is going to be, this k4 is going to range over all our possible momentum values, which we generally have been assuming is discrete. So this K4 will range over everything, P3, P4, P97, and also P1 and P2. So here's a K4 acting on that part. That it will basically always equal 0 unless K4 equals P1 or P2, because you're destroying a particle that doesn't exist if K4 is not P1 and P2 in that sum. So when it's not P1 and P2, this whole thing will just equal 0. That won't contribute anything to an amplitude. 0 doesn't contribute anything. So that forces K4, if we're going to calculate anything that means anything, to equal either P1 or P2. Let's just suppose for this calculation that K4 equals P1. We're going to generalize this later and include all possibilities, but just for now, let's say K4 equals P1. So what happens now? We're just going to crank through this calculation, starting with this part. If K4 equals P1, especially since these are not relativistically normalized, it's very simple. It just destroys this particle, and we're just left with a single particle state P2 That other one's gone, so that's what we get here. We already used this operator here, so that's not included in this expression. Then we keep going. Same thing applies. Here's AK3 applied to P2. If AK3, which takes on a sum, it's still the sum of all possible p-values. K3 is ranged over all possible p-values. If that's not equal to P2 during the sum, that'll always give us 0, so that won't contribute. So let's just look at the case during the sum when K3 happens to be equal to P2. That's the only thing that could potentially contribute, and that gives us this over here. Next step, AK3 kills this and just gives me the vacuum state, and now I just have these two left over in this brow over here. So that's what I got now. Well, now look at this expression here. Now I have AK2 acting on a vacuum state. This AK2 again is summed over all possible K2s, but as we know, it doesn't matter what K2 is here, a destruction operator acting on the vacuum state will always give me 0, not the vacuum state 0, but the mathematical number 0. So this whole expression will basically end up always turning out to 0 when I have a term like this. So that really can't contribute anything to our transition amplitude for scattering. So these terms of this sort, which we've looked at from the previous expression, came back from our first order term, won't contribute anything, so we can ignore that. Here's another term that I showed before when I did that binomial expansion that has one thing daggered and the other 3 next to it are non-daggered. What about that? Well, just for practice, we can kind of look and see what happens here. We hit this AK4 over here. Again, there's a sum over all these Ks, and that can only be non-zero if K4 equals P1 or P2. Let's just suppose it equals P1, so that kills this state. A destruction operator acting on this 2-particle state will kill this if it equals that, if K4 equals that, and just left with P2 over here. Or if this AK4 here, I wrote it kind of differently mathematically, equals P2, it'll kill that and leave us with P1. So technically, since the whole thing is a sum, I would actually get this as an equal sign. So here I just wrote it a little differently, which still works out mathematically. Then moving forward, the next thing is have AK3 hitting this P2. Everything will be 0 except the one time when K3 in the sum equals P2, and that'll just knock that out and give me the vacuum state with no particles. That's what I got here. And on this side, I can do a similar thing. This AK3 equals P1, and I'll just get the vacuum state there. But then, regardless, I have this sum plus this sum. Now, again, I'm back to the same situation where I have a non-daggered acting on the vacuum state on both sides. And what that ends up just giving me is 0, mathematical 0. Therefore, terms of this form do not contribute at all to the transition amplitude, as I just showed you. What about if the dagger is moved to the right? Well, basically, you can take your time and just start cranking out these calculations. If this dagger is moved to the right, then I have an interesting situation where I have a sum over K4. So technically, I'll have all 3 particle states in this calculation. That K4 ranges over all possible potential momentum values. P1 and P2 are unchanged. Then I'm going to hit it again with K3. And this AK3 is going to hit this, and the only way that this thing won't get annihilated is that if K3 equals either K4, P1, or P2. So let's just say AK3 equals K4 in the sum. That just gives me P1, P2. Then I have 2 more destruction operators that also have to equal this and this, so I don't get a non-zero result. They don't actually equal it, but I get 0 every time they don't, so it doesn't show up in my calculation. So let's just say K1, K2, and K3 all end up matching this. Then the best I can do without killing this yet is to get the vacuum state here. And then I have no more operators, but I have a vacuum state taken, its inner product taken with this Fock state over here. Now, as you remember, these are both Fock states, and the inner product of any 2 Fock states that aren't the same is always equal to 0. If they're the same, it's equal to 1, but if I do relativistic normalization, it's a factor, another constant factor multiplied by 1. So this gives me 0. So even terms like this will still ultimately give me 0. So that's what this is stating here. Now, what you learn from this calculation is that these things are going to keep hitting this over here, and that's very beautiful formalism that we have where A and A daggers create and destroy particles, and we have this simple interpretation of this as a 2-particle state. Remember, we've talked about that a lot in the lectures earlier when we developed this whole theory, and the A's and A daggers act in a very beautiful and simple and kind of neat mathematical way to create and destroy stuff. But ultimately, this whole A dagger stuff is going to affect this thing and give me some new ket after all of it's done. That new ket is going to be taken, its inner product is going to be taken with this original bra of the final state. And basically, what the only way I'll get a non-zero answer is if I can manipulate all this stuff and I get the final thing at the end that equals the original thing. So I'm gonna, even if I do a bunch of manipulation, I may get something with some constant factors that I'm ignoring right now that get pulled out front that actually matter for our calculation. But basically, in terms of the kets and the bras, the bra is always Q1, Q2. So whatever I get on the right after I act on it with all these creation destruction operators, in this case was zero, but it has to be actually really has to match this, and P1, P2 actually has to be Q1, Q2. Um, Otherwise, we're going to get zero. So this P1, P2, after all the manipulation, has to equal Q1, Q2 to get any kind of non-zero answer. And I'll get one there, but then I may have some constant factors that become relevant in our scattering. So that's the rough idea here. So after you look at all of this and realize what I just said, basically, the only way I can start with two particles and get something like this at the end, which is my only non-zero answer, is that I have to get two particles back. So if all these combinations of an A and A daggers, I basically have to have two A non-daggers, two destruction operators to destroy these two, and then two creation operators to act on the vacuum and recreate two particles. And the only way I can have this matching the final thing here is that if they both have two particles. And that requires two A daggers and two A's. So in all these all these things are four terms here from that binomial expansion. The only ones that are going to give me anything potentially non-zero is when I have two of these A's are daggered and two of them are not daggered. Otherwise, we're going to get zero. By that same argument, remember I had all those five things listed from the binomial expansion that were just representative. The other thing that I wrote by 3, you can go back, also equals 0. So the only ones that are going to give us any kind of actual thing, I mentioned 1, 2, 3, 4, and 5, if you remember from before when I expanded it out binomially, are the different types of terms. The only kind of terms that could potentially give us a non-zero answer are things where you have two daggered and two undaggered A's. And that's something like this and something like this. Here I have the daggers all the way to the left and the non-daggered terms all the way on the right. And here I have them kind of spaced apart, one after the other, alternating. And any other thing, there's more than this too. I can imagine dagger here, no dagger here, two daggers at the end, so on and so forth. So theoretically, these are the only things that can give me a non-zero answer. Let's look now in great depth at 4, anticipating that this may be one of the most relevant calculations because it may give us an answer that is not zero. So let's look at this calculation here. Again, we are simplifying our overall calculation by making these non-relativistically normalized, pulling out factors, not always including all the other factors, but this is what we're dealing with. And this you can still imagine as a sum over K1, K2, K3, and K4. That's the original calculation, but we're going to calculate this guy here. Let's just assume, so AK4 now, acting on this, will always be 0 unless this K4 equals this particle or this K4 equals this particle. Let's just assume this is going to equal this. We'll take care of the other possibilities later when we count different possibilities. But just for simplicity to move forward, we're going to assume K4 equals P1 right now. So if this K4 equals P1, remember this is a sum over AK4s. All of them are going to be 0 except when, let's say, K4 equals P1. And in that situation, a destruction operator will knock out this out of this two particle state. I'll knock out P1, and I'm just left with P2. And then I just have this remaining expression. Now I have a K3 acting on P2, and same argument, this has to equal that to get a non-zero term. And when it does, it knocks that particle out, so I'm just left with the vacuum state of no particles and this expression here. Now I can act on it with the daggers, and I still have a sum, an implicit sum over K1 and K2 here. And this will kind of create a sum of various different particles. If you look at that, it's going to create a situation where I have all possible ranges of particles K2, because I have a sum here, so it's going to have P1, P2, P3, P4, and every possibility. But ultimately, if you remember from the previous calculation, this, after I'm done hitting it with 2 of the daggers, has to equal this. Otherwise, even if there's 2 particles here and they're different than these 2 particles, the Fock inner product of 2 different states is always 0, even if they're two particle states with different momentum. So the only relevant term that's going to survive is when this a dagger K2 out of summing over possible all momentum values K2 is when it actually equals Q1 or Q2. Let's just assume it equals Q1. And then when that happens, I'm going to get this term here, Q1, where I have one particle state now, Q1. And then I'm going to hit it again with this A dagger K1. And the same argument again applies that, yes, it'll be technically a whole sum of two particle states with different K1s, but they'll all equal 0 except when this whole thing, after I act on it, gives me Q1, which Q2, which acts on this. So let's just say K1 here equals Q2. And then I will just get this over here. And then I finally get the number 1 because the inner product of this equals 1, and that's not 0. So I'm going to get something that actually survives with this thing over here. And that's the rough idea of how it happens. We can get to the details shortly here. Now we're going to get to the next slide and talk about all the stuff that we pulled out of these inner products. So the answer won't just be 1, but this gives you a big, broad overview of the nature of this calculation. Please take your time, work through this yourself, review these lectures a lot. It's kind of fun calculations when you just realize the A and A daggers are literally kind of creating and destroying particles. They're doing it mathematically, but it's a very cool physical interpretation. Now we get to things that look complicated, but they're not. If you just, they're easy to make dumb mistakes. And, please point out if I've made mistakes in all of this, because I easily could have. But that's just nature of being careful and following through the big principles we just spelled out. So here we go. We're still now going to do this full calculation over here. Remember, we can pull out these factors minus I lambda over 4 factorial. This integral over d4th x I pulled out. Then we're going to expand this like we did before. Here's the expansion, 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 expansion. Remember, in each of these expansions, there's a prefactor itself of 1 over the square root of 2 times the volume of our box that we're interacting with, spatial volume of our box, times these factors of 1 over the energy, the square root of omega K1, K2, K3, and K4. Just remember this expansion. All of those factors I'm going to pull out over here with some of this other stuff. This is still within a sum, and that's what I get. Now we'll see some more manipulation, but remember, this is still relativistically normalized. It's nicer, even though you need to deal with relativistic normalization, as that's the mathematical representation of our actual physical state. It's easier to sometimes have arrows on these, in which case there's more factors of radical 2 omegas that we get pulled out ultimately in the front. And the only, out of all of these expansions, we are picking the one that has 2 A daggers from each of these. You have to pick an A dagger, and then just 2 ones that don't have daggers, the regular A terms. And the way we picked it is A dagger and A dagger from the beginning. So we'll pick an A dagger here, an A dagger here, just an A here, and A here. So if we do that, we get something like this. I tried to keep things a little bit color-coded, make it a little bit easier to follow. So here's where I got this A dagger from. I picked out of this first binomial term, I just picked this guy here. I still now I'm keeping my E exponential, e to the plus I k1x. Remember, I have k1, k2, k3, and k4. I just labeled them as independent k's. This A dagger goes right over here. This A non-dagger goes right over here, which has a minus k3x. That's just based on the expansion. That's why this is minus, this is plus. And this non-dagger term goes right over here, a k4 e to the minus I k4x. And then I still now sandwich it. I convert this now to non-relativistically normalized. It's just a little easier to deal with, I think, here and here. And then if I do that, I have to pull out these factors of square root of 2 omega p1, square root of 2 omega p2, because that's the relativistic normalization. But I can pull that out of everything and pull it up front right over here. And I do the same thing with this. I make this non-relativistically normalized and pull the factors out there. And that's in addition to all my other prefactors I have here. So now here's what I got there. That's just explaining the relativistic normalization part I just mentioned. So now let's crank this part out over here. So I have AK4 acting on this over here. These are just numbers. So these don't really matter. You can actually pull them out of the inner product and just look at the operators. So AK4 acting on this, that'll always give me 0 unless K4 equals P1 or P2. Let's just assume that K4 equals P1 in this case. We'll figure out the other possibilities later. We'll add them up combinatorically later. Let's just suppose K4 equals P1. So it's going to, this destruction operator will act on this and kill this state. and just leave me with P2. So what you see here, all my other factors are still there. What's interesting is that this K4 is, this is all a sum over K4. This whole thing is going to sum, and you're going to keep changing the values of the sum of K4 and this exponential. So it's going to range, K4 itself will range over all the momentums, but all those factors will be zero except the time when K4 equals P1. So that turns this generalized K4 into minus I P1x, because that's the term that survives. So that's what I pulled out over here, e to the minus I P1x. That's the only one that survives. And similarly, I also take this sum over all the possible energies, omega K4. That's part of this whole original sum. And again, every part of this will die out except when K4 equals P1. So that's why I just switched this factor here to omega P1, and I can pull that out now of this whole sum because the sum is over all K's. This is not a function of K. That's where I got this new prefactor, which will matter. This becomes e to the minus I P1 and 1 over omega P1, which I pull out over here. The rest still stays the same. Now I still have these three factors that I didn't use yet, and then these three terms over here, and all these other prefactors. And the sum now collapses to just K1, K2, K3. We just did the whole sum over K4. Same argument applies. I'm going to hit AK3 on this state P2. Everything will be 0 except when K3 equals P2. So that's going to force this K3 of all the sums, that K3 will equal P2. So that's why I pull this out over here. There's still that minus sign, e to the minus I P2x. This is still the same x since these were all taken at the same spatial point, space-time point x. So that's still there. And then that prefactor I talked about over here, that omega 3 is going to be forced to be equal to P2. So I just pull that out over here out of the sum. I still get all this other stuff still the same. And now I'm just down to two different sums, K1 and K2, like this part over here. This omega got pulled out. And I still have this over here, and I just use this guy up. So now I'm over here. Now, again, I'm going to just hit this with this A dagger. Remember, these exponential factors are just numerically important, but they have nothing to do with operating on kets. They're not operators, they're numbers. So you can just pull them out of this inner product if you want. But this A dagger, K2, acting on this will give me a whole host of part one particle states ranging throughout all of K2 as K2 ranges out through all the possible momentums. But ultimately, all of those are eventually going to be zero except when this K2 and this K1 give me Q1, Q2, because I'm just going to get a two particle state, and that two particle state has to match this perfectly to get a non-zero result. So I'm just going to assume now K2 equals Q1 in this case for this reason here. We've talked about that before. And then this, we'll just do two steps at once. This K1 also has to equal, in this case, Q2, and you can do it the other way around. We'll account for these combinatorics later. But basically, that's the only combination when this K1 and K2 give me equal Q1 and Q2 in the sum. That's the only time I get a non-zero term. And that's what allows me with this inner product, which is non-zero. It's actually 1. And then these factors, K1 and K2, if you just follow through the math, will be forced to be Q1 and Q2, which is here. And now there's a plus sign because this came from a dagger, which also has a plus next to it from the original phi expansion. And I get A plus Q2x, E plus IQ1x. And same thing with these factors. These are going to be forced to be Q1 and Q2, which I just put over here. And everything else is the same. I've gotten rid of now. I've used all my sums, so this is what I finally get over here. We'll keep going through the calculation. A lot of things will kind of simplify here. This inner product is identically 1. Remember, we're using the non-relativistically normalized Fock state here, which is nice because it just equals 1. All of these omega factors in this first order calculation nicely cancel. So this, and this will cancel this whole thing. So that just cancels out. And we're left with this pretty simple thing where I took the minus I lambda over 4 factorial v squared. The v's are going to give me square root of v times square root of v, which 4 times actually. Sorry, I didn't possibly put that all in here, but I get square root of 2 4 times divided by the square root of 2 4 times. That'll also cancel, and then I get the square root of v on the denominator 4 times, which is basically square root of v times square root of v, which is v, and then it's times itself again, which is v squared. That's where that comes from. I can just manipulate stuff because this has nothing to do with x. I'm going to pull that out of the integral of x. This has to do with x, all these terms, and I get that here. And these exponentials, of course, combine as exponentials do. These are all numbers. And I can write it like this, e to the minus I p1 plus p2 minus q1 minus q2, parentheses closed, x. So this whole calculation of this term here is just shaking down to this here after some pretty neat calculations here. And now here's another important part. You may recognize this as something very similar to what we've talked about before. Look at lecture 6i. We talked about it in the three-dimensional form. This is a four-dimensional form. And if you remember from lecture 6i, this thing over here is nothing but the Dirac delta or Kronecker delta function, depending on if you use continuous or discrete representations. And we go back and forth kind of between them for pedagogical reasons. And that's what we find here. We can extend the definition, which technically in lecture 6i was in 3 dimensions. You can naturally extend that to 4 dimensions, including time. And you would get this, that the integral of this whole expression over d fourth x, and this is a 4-dimensional x, of this basically just gives me a delta function. In this case, I'm going to use the discrete form, which is different than a lot of books, but a little bit easier, the Kronecker delta. And this delta basically means this whole thing here will have to be 0. So here's how you can write that with the Kronecker delta p1 plus p2 minus q1 minus q2 comma 0. And then times the volume of everything here, which is the three-dimensional spatial volume, v, times the time volume, which we call t. You could even call it L, because we kind of assume t and L are the same. But t, capital T here, does not represent the time ordered operation, just represents the whole time of the difference between TF and TI at the whole time of our interaction. So that's what we get for this. So that whole thing will shake down to this. Roughly, just try to remember why this is true. If all of this stuff here equals 0, then e to the 0 is 1, and we just take 1 and we multiply it by the whole volume, space-time volume of our box, all three-dimensional volumes plus the whole time, and you just get vt. If this is anything other than 0, this whole thing, then you just have the sum of allowable momentums minus 2 other allowable momentums, and you just get another allowable momentum. And we decided, if you look way back in our math, somewhat tedious, but important, that we only use momentums that fulfill complete cycles or partly complete cycles inside of a box of space and time, and that whole thing ends up being 0 because they perfectly integrate out to average out to 0. So that's why you get this Dirac delta. You can look at this lecture 6i again for a refresher on that if it's not clear to you. So this whole thing just becomes this delta function, and this is our close to final answer here. I get minus I lambda over 4 factorial times 1 over v squared, and then this thing here, which is just vt, and this in this place I wrote it as a Kronecker delta. I could even change these minus signs a little. It just says that this whole thing has to equal 0. So that's what I did over here. I just kind of re-expressed as I canceled out some of the v stuff, and depending, other books may have a different calculation. They may not use discrete formalisms. At least the way we're doing it, this is what I calculated. You can tell me if I made any mistakes, but this big picture is what's important here. When we get to quantum electrodynamics and real calculations, we'll try to be very careful and have to be somewhat consistent because there's actual experimental data we have to see that we're matching with. So there's minus I lambda over 4 factorial, t over v, and I just rewrote this as this, which is the same thing. I said that p1 plus p2 comma q1 plus q2, meaning that this has to equal this, then I get 1, and when this is not equal to this, I get 0. So just to be consistent with some other books and lecture notes that you may find online, the discrete form answer that I calculated is this over here, and that comes from assuming this number here is equal to this Kronecker delta. A lot of other books will just go right to the Dirac delta and assume that this whole integral is the Dirac delta. If you do that, instead of factors of L, you get factors of 2 pi. That's just the way things work with Fourier transforms and things like that. In most books, this would be the convention. So instead of the VT, you say 2 pi to the 4th power. So every time you see L times L times L times L, instead of replace L with 2 pi and get 2 to the 4th, that's how you convert readily between these two. That's just a detail that's not that important. Don't worry too much if you don't understand me, but you can just express this whole thing in terms of a Dirac delta over here, which is like this, rather than a Kronecker delta if you want. And they're both important formulations to know. Most books will express it like this for now. I like this a little bit clearer just for where we're at right now. So if you wanted to express this final answer in continuous form, you would get something like this: minus I lambda over 4 factorial 1 over v squared, and these factors here. Even these v factors you can kind of wash out or express differently depending on multiple levels of discretizing or doing continuous forms, but that's just what we're going to write here. So this is our answer that we're getting here after for our transition amplitude. Remember, this is describing the result. We haven't fully calculated everything, but the result of an experiment where we have two particles. We want to see what's the chance of getting two other particles, potentially of different momentum. And this is our answer. But now you have this delta function, which might be infinite. Is that a problem? Not really, because if you use the delta function here, later you're going to integrate over all possible continuous momentum, and it'll work out perfectly. This delta function only becomes infinite because your potential momentum values are changing from discrete to continuous, but it'll all factor out fine. So this is not a problem, is all I'll leave it at. This quote unquote infinity from this delta function. So that's no problem. It will wash out if you use the correct formulas. If you use this, you don't have to think about that, as we can. And that's what this kind of nicely shows also, that you don't have to think about any potential infinity lurking here. Now, what does all this mean? Well, this is huge, actually. This says that in our theory, which we didn't assume that nature consists of just particles fundamentally, but we started with just a ball on a 1D track and one of those at each point in space. And we built up to this very elaborate theory with very simple physics principles being followed, not adding a lot of ad hoc stuff at all, if any. We talk about simplicity and everything else. And we still came up with an idea where we can see what fundamental particles are and now how they interact. And what we know from every single collider experiment that has ever been done, total momentum before the collision equals the total momentum of stuff you observe after the collision. And same thing, total energy before the collision equals the total energy of all the stuff you observe after the collision. This is an experimental fact that you will always see, even as particles are being created and destroyed and things are potentially changing direction. What you'll always find is that if you started in an eigenstate of having particles that have a certain total momentum, every single measurement you do, even though each measurement may have a different outcome, every single one of those outcomes, each individual outcome will always have total momentum and total energy conserved. And this is what we're finding exactly in this calculation. Now that we've gotten some more complicated answers, we get these delta functions. And these delta functions are showing us that we have complete conservation here. Apologize here. I think I wrote this in different ways. You can just say that this one is a regular delta function and this is a Dirac delta function. It doesn't matter, but the whole point is the delta function here will equal 0. Remember, P1 and P2 are our initial momentum and energy. These are 4 vectors, and Q1 and Q2 are our final momentums and energy. And what this shows is that the total initial momentum and energy has to equal the total final momentum and energy, whether you use a continuous Dirac delta or the Kronecker delta. That's what we get. You have this other factor over here. But in all of our experiments here, we are finding that there's true conservation of momentum and energy in any kind of particle experiment here, at least for 2 to 2 scattering. If you ever have a situation where you're trying to see what are the chances of starting with P1 and P2 and ending up with Q1 plus Q2, or the sum of the two are not the same, the chance of that, according to our calculation here, is totally 0. We're not going to show it, but basically we can prove that this is true to all orders. When we get to the second order calculation, third order, 57th order, we'll always find that this is true, that momentum and energy are always conserved. Whatever you start with is whatever you end with, even when you have 3 particles and 4 particles and things like that. In fact, at least when you look at the continuous representation, which now, to be consistent with books, we'll have to do a lot of that also, you'll always find this delta function, and then you'll find the initial momentum and energy minus the final momentum and energy, and it'll always be the case in your calculations, and this factor of 2 pi to the 4th, which is kind of a volume factor. You'll always find this factor coming into play every time when you do these calculations. So because it's a trivial part, it's not trivial, it's a very important physical finding that really shows that our theory really nicely is mimicking reality. But as far as the calculation to try to figure out different scattering amplitudes, you'll always get this factor. So physicists have kind of factored out this part here and says, I really care about this part. And that this part over here, so this whole thing divided by just this factor you'll always find in your calculations gets rid of this. And this part here that's potentially different and interesting for each experiment, they call the Feynman amplitude. And so in this case, for this sub-calculation, our Feynman amplitude, we haven't calculated all the dimension possibilities is minus I lambda over 4 factorial times 1 over v squared. Okay, so how about we talked about the fact that we needed our terms to always have two A daggers and two A non-daggers, two creation, two destruction operators. In the previous calculation, we showed the result when we have A dagger, and then A and just A. What about other things where you still have two A daggers, but they're not exactly in the same order as what we talked about before? So let's look at that here. I'm going to try to go a little bit fast just to kind of give you the general gist of this. And I'm also going to not worry too much about some of these other prefactors just to give you the gist of what happens here. In other words, you have two A daggers, but they're not A dagger, A dagger, A. This one's A dagger, A dagger, A. So if you do this and you work through the math, which we'll do somewhat quickly, take AK4, it's going to knock out one of these, and all the statements we said before that it's technically a sum, and you have to pick the right one, and we're just picking one of them is what we're going to just assume here. But you take this AK4, it knocks out the P1, and you're left with this over here. You have A dagger over here, K3, and you have these prefactors that get pulled out, e to the minus I P1. Then we keep cranking through everything. Let's see, AK3. Now that is going to act on this over here. If that happens to equal Q1 or Q2, then you can crank this all out over here and you'll get a number that's roughly proportional to 1. But when K3 is not equal to Q1 or Q2 to begin with, then you get, it's not equal to Q1 or Q2, then you're going to get something like this, where this A dagger acts on this, and you're going to get the whole range of states K3, P2, two particle states, but the sum is still not collapsing, is everything K3 to P2. And then if you keep cranking things out again, you have this K2 that if it's not equal to one of these two things, you get 0, but the contribution that's non-zero would come from K2 equals K3 or K2 equals P2. Continuing this on the next slide over here, if you keep doing that and K2 equals K3, let's just assume that. Well, all these things are part of the sum, so you're going to get all sorts of terms here, but we're just picking various terms to keep looking at. So let's say this K2 equals K3, then that's going to kill this every time. It's going to do it for each possible K2 hitting K3, and you go to the range of K2s, and you still have the original sum of K3s. So those factors are going to pull out here. You have e to the minus I P1x, which is there, and then you still have the sum, and then you have minus I K3, and then this K2 becomes K3. It equals that exactly. It's still within this sum of 1 to 3. Now you collapse the sum K2 because that just became K3, so that sum is gone. This is just the sum of K1 and K3. Now you're just left with this term over here, and then you've killed this. So this is P2, and this is this over here. Now, the only non-zero contributions here are going to be when A dagger K1 is P2. Sorry, the contribution will be A dagger K1 is going to go, through the entire contribution here over the sum of K1. And when you do that here, you get this K1, P2, and now you're still taking the sum over K1. And you have all of these states over here. This K1 can get pulled out as just K1 over here. Let's look at this over here. When you're analyzing this whole thing, if this whole thing will equal 0 unless K1, and it won't have any contribution for those situations, but it'll equal 0 unless K1 equals Q1 and P2 equals Q2, or K1 equals Q2 and P2 equals Q1. Now, K1 is part of a sum, so you have to sum over all the values. So you really don't, quote unquote, have control over it mathematically. At one point, it will equal Q1 or Q2. Let's just say Q1. But Q1 and Q2 is something you choose to calculate. You want to know what are the chances of it being such and such two particle state, and that you can, quote unquote, mathematically control because you pick what answer you're looking for here. Now, all of this will vanish unless one of the final particles equals one of the initial particles. And basically, this whole thing will always equal 0, except in those situations where one of the final particles equals one of the initial particles. And that's called forward scattering. That's the term I think people use when you have a scattering event in one of the particles is exactly the same as it started at the end. Now, let's just assume P2 equals Q2. Then you're going to get this expression over here where P2 equals Q2, and you still have K1, and you have this sum still over K1 and K3. Let's flip this to the next slide so we can see it. Here's the same thing expressed again. Now you have that sum over K1 and K3. But this sum, the K3s over here you're going to see are going to cancel. Not cancel, but these these exponentials can be added, and that'll be e to the 0 or 1, which we'll do in a second. But before that, the only non-zero terms for this whole expression are going to be when K1 equals Q1, because if it wasn't the case, then these are two different Fock states which are orthogonal, and that gives you 0. So when we do all of this sum, you're still going to have the parts that survive where K1 equals Q1. So that collapses the sum over K1 and makes this K1 equal to Q1. So you just get this over here. Now this thing here is now the two of the same state. So it's 1, non-zero, but it's 1. And what about here? Well, now here's where we're going to do the part where we have the K minus K3 and e to the minus I K3 and e to the plus I K3. You can add those two to get e to the 0, which is 1. This sum, very importantly, still stays. Nothing we've done collapse that sum, the sum over K3. And these other factors get pulled out over here, e to the minus IP1 plus e to the plus I Q1x. And then just keep cranking this out. This part here is still going to give us some sort of a delta function, which is ensuring that P1 and Q1 are the same. One of the particles is totally unchanged. And then you get this factor over here. This thing will just become a delta function. Here we express it the the Dirac delta to be continuous, but you could have done it the other way, and you get this final contribution here. Now this is the problem here. This delta function we talked about, we can always kind of wash away, but this part over here is not something we can wash away. We're summing the number 1 over and over and over and over again over all the possible momentum states K3, and that number is basically infinite, or even if you just allow for only a certain finite number of momentum, it's an enormously huge number because you're just adding 1 to it every time. That quote-unquote infinity is a problem in this calculation. What this physically means is that the chances of having forward scattering are nearly infinite, and that's not even worrying about this delta function. So this is a problem in our calculation, that if we wanted to see a situation, look at all the different situations, we would basically get infinity, which is overwhelmingly large for no scattering, or at least if one part forward scatters, that situation would be infinite, and there would be no other possibility for anything else, which is contradicting our experiment. We can't get infinity for one of our potential scattering situations and nothing anywhere else that matches experiment as you get up to this order over here. Of course, for the first 0th order, then you have that situation, but here you should have other situations also. So this is the problem. How do we get out of this problem? Well, here's the actual solution. We realize this is not going to work, so we actually have to very slightly modify our interaction so we get meaningful results. So instead of saying our interaction Hamiltonian in this toy model, which is still a toy model, is lambda over 4 factorial phi to the 4th x, we are going to make a subtle change and say that this is not the actual interaction part of our Hamiltonian, but this is it. Lambda over 4 factorial normal ordering of phi to the 4th x. So these two signs, these double dots on each side means normal ordering. So remember, in the toy model, we created an interaction Hamiltonian somewhat arbitrarily to kind of see what happens when you add interactions. This original Hamiltonian was created by special arguments of special relativity, symmetry, simplicity. This part was somewhat arbitrary, but this somewhat arbitrary part, if we just do it, we're going to get nonsensical results. So we just change it slightly to saying normal order right from the beginning. This doesn't actually change our previous calculations, but it will help right now to get rid of this infinity that keeps creeping up in our answer. And this is, of course, I just directly expressed it in the interaction picture rather than get back to the Schrodinger picture. How does it get rid of infinities? Well, let's just quickly review what we mean when we say the normal ordering of a product of operators like this, where one is a creation operator, the other is a destruction operator. Normal ordering means, by definition, we always take the destruction part and just arbitrarily force it to the right and keep the construction part or the creation operators to the left. That's what this means. You can do it on this kind of expression here where normal ordering is understood to be linearly distributed. You can do the binomial FOIL on this to expand out these terms, and each of these is considered normal ordered. So this one won't matter. There's all destruction operators, so there's nothing different, so get rid of the normal ordering signs. For this part of the expansion, you have a destruction operator to the left, so you normal ordering. After you've expanded this and applied it here, forces this term to change to this with the destruction operators to the right, the non-dagger term. This one is okay as is, so the normal ordering has no effect. This one has no effect because they're both the same creation operator, so that stays the same here. So why does this help us? Well, remember, these expressions, we did a long calculation, have a very finite contribution, and it's something like I lambda over 4 factorial 1 over v squared, depending on how you calculate it. So these ones are good where you have the dagger, dagger, no dagger, no dagger. But our problem expressions were this, where you have two daggers and two non-daggers, which is good, but you now don't have them ordered this way. You have, for example, interspersed non-dagger, dagger, non-dagger, dagger. And this is what caused the problem with forward scattering, which was one of our transition amplitudes that you could theoretically carry, get essentially an infinite number of terms like this. But when you force everything to become normal ordered, so that you use an interaction Hamiltonian with the double dots instead of just one without it, then these terms will all get normal ordered, and that'll force you into this scenario over here where you have a dagger, AK1, AK4, and we know from our calculations that this gives finite answers, not an infinite answer acting on it. As you can do all of these sums and realize, just go through the calculation we just did, and you realize that fixes the problem. And this gives us a finite answer ultimately over here. Now, we did quote unquote one type of thing where you have two daggers and no daggers, and the daggers were right to the left, a dagger, A, and A. But there's still more than one way to get the a dagger, AA form. There's several terms in our original binomial expansion. We took our binomial terms 4 times and multiplied them out. There's still several ways to get a dagger, AA, and let's count them. And we have to include each one of them in our actual answer. So there's some combinatorics about how many different ways can you form something of the form a dagger, AA. So this is kind of the problem. It's a combinatorics type question. Here's what we're trying to basically calculate: Q1, Q2, and then let's just put this here: P1, P2, and then I just want to figure out with these question marks, we want dagger, dagger, no dagger, no dagger, and how many different ways we're going to do it. Remember, because we're normal ordering our Hamiltonian after all that we don't have to start by picking dagger, dagger here. We can even put daggers here, dagger here and there, and the normal ordering part will automatically fix this back to the form that we like. Sorry. So how do we choose this out of the 4 A's with the question mark, meaning that we're either going to leave it nothing or put a dagger on it? We have to pick 2 of these to have a dagger, the K1, K2, K3, and K4. So the problem will be 4 things, choose 2, and combinatorics says that we just do this. That's 4 times 3 over 2. That's how you have 4 objects and you pick 2 of them, where the order in which you pick them and arrange them after you pick them doesn't matter. So you get 4 times 3 over 2. That's our first choice. Then we pick one of the 2 daggers to be Q1. Remember, they're going to ultimately act on a vacuum state, and we have to recreate this state to get a non-zero term. So we're going to have to pick one of them to be Q1, and the other one will automatically be Q2. So you have a choice of which of the 2 daggered ones that you picked to associate with Q1. So that gives us 2 more choices. Then of the non-dagger terms that are remaining, then you have to pick one of them to be P1, and the other one will automatically be P2. So you have 2 more choices there. And then remember, we did the whole calculation. If once you have done this in your normal order, you have something like a dagger, AA. And each of those, we did the whole calculation, yields a factor of minus I lambda over 4 factorial times 1 over v squared. and now it's identical. And so you have to take each one of those and add them to all the other ones. And how many other ones were there? Well, if you multiply all these combinatorically, you know. So if we add up all the terms, we get our final Feynman amplitude S1 contribution, and that's, we have this many choices, 4 times 3 divided by 2 times this many choices times 2 times this many choices times 2. And then here's how much we get from each one of these calculations when we do it. We add them all together, so it's this, the total number of choices multiplied, which is this, multiplied by each amplitude for each term. So the final amplitude will be this. The factorials will nicely cancel out. You have 4 times 3 times 2 factorial, and that cancels out with this. And then you have 2 over 2, that cancels out to 1. And this is your kind of final answer for your S1 contribution. The S1 term contribution to your final Feynman amplitude is minus I lambda over v squared. If you, the v squared part you'll see not included in certain textbooks depending on how you define discretized calculations, but the minus I lambda seems to be the really important part. So the physical interpretation, remember we just calculated only the S1 term. We still have to add the S0 term, because if we're working the first order, we do the first zeroth order plus the first order, not just the first order term, so fine. I can present this thing in different ways, but this is kind of maybe a logical way to do it. Just think of 3 different possibilities that I have exactly Q1, Q2 equals P1, P2, i.e. there's no scattering. My output is exactly the same as my input. That's possibility 1. Second possibility is that my output is not equal to my input, but I still do have total momentum and energy conservation. Q1, Q2, Q1 plus Q2 equals P1 plus P2, but they might not be exactly equal. Or they might not be exactly equal. And the third thing is I have that they're not equal, but there is no momentum conservation, that the final output state is different in terms of total energy momentum than the initial input state. So if we now just crank out our calculation and realize the full calculation is to first order is not just S1 with this thing sandwich, but S0 plus S1. And we just look back at our previous results. For the S0 contribution from here to here, we have this expressed this way. We showed this briefly on one of the earlier slides in this lecture, that this whole form is like this. And then for the S1 calculation hitting here, we just spent all that time explaining it, that the final contribution after you add all the Feynman potential contribution, Feynman amplitudes, is going to be this right over here. Now, if you look at each of these scenarios, for the first scenario of no scattering, that's going to make us have a contribution of the whole thing plus this whole thing. And this thing basically says that they're equal, so one of these will cancel, so it'll just be left with, so either I have P1 equals Q1 and P2 equals Q2, or just P1 equals Q2 and P2 equals Q1. But basically that will just give me this for SFI, for my transition amplitude, 4 omega P1 P2 minus this contribution. So this is my SFI for this first possibility. For my second possibility, I'm just going to have the first part, this term will not, because these two states are not exactly equal, this whole thing will cancel out. I'm just left with this part over here, which is minus I lambda T over V. And this delta function, because I do have momentum conservation, my second possibility will just give me 1. So that just doesn't show up here in the calculation. And the third possibility is always 0. The possibility of having no momentum conservation will always be 0, whatever terms you look at here to first order. So in order to figure out probabilities, technically I have to convert the SFIs to probability of FI, which I call PFI. All I have to do is take the complex modulus of these things and square it according to these formulas. So that's pretty easy to do for this complex number. You take its modulus or multiply it by its complex conjugate, and then that squared is automatically equal to this, which is over here. So that's the final probability of getting this first result where you have no scattering. And same thing with this SFI. I can take the complex modulus of that, consider the I, and just take the real component here, which is lambda squared, t squared over v squared once I square it, and this 0 squared is still 0 squared. So these are my final probabilities, or technically the probability ratios of seeing those 3 different possibilities of scattering. Remember, the ratios are what's important. We can always normalize it if we want, so that everything equals 1. You can figure out how to do that once you know all the things. physical interpretation is basically this. Now up to first order, the chances of ever seeing a situation where you don't have momentum and energy conservation is zero. So this is our prediction up to first order, that if you do your particle accelerator experiment, that you will never see a result that has no momentum conservation. That's consistent with our experiment. So the theory is very good so far. The highest thing that you can observe, which is out of these three numbers, this is the biggest, is going to be no scattering, where you put in two particles and you pretty much get exactly the same two particles out with no scattering. Those are the situations you're going to see the most often. How often? This often. At least this compared to that is the ratio is going to be important. And then we'll also see some cases where there actually is scattering, unlike zeroth order. We'll see some situations where you do the experiment, there is scattering. And when you see the scattering, there'll always be total momentum and energy conservation. And among those cases, there's actually going to be equal outcomes. So even here, you're going to find that if you're talking about, my final outcome is a particle going this way and a particle going this way, which might be scattered from what you had originally. And if you say, what about the chance of another particle going this way and one going this way? Those results are always going to be equal. That's what this says. There's nothing within this subset that makes one different than the other. The only thing that matters is these factors, lambda, um, t, which is the time of interaction, and the volume of our base, which don't matter at all. So you're going to see different scattering things, still obeying momentum and energy conservation, but you might see some scattering this way, some scattering this way, some scattering another way. And those outcomes are going to be equal. Whether things scatter this way or that way will be equal. And that does make some sense for a theory of scalar particles where there's nothing intrinsic like spin that prefers a particular direction. When we get to things like quantum electrodynamics, there you'll see that there is a very angle dependent result. Like you'll see scattering certain angles with respect to your initial collision angle, collision axis. But here the results are going to be exactly equal the same. So that makes sense. So in summary, we use Dyson's formula to calculate the zeroth and first order scattering terms, S0 and S1 for 2 to 2 particle scattering. A lot of tedious calculations, but still hopefully straightforward. So there's a long set of lectures because I'm just going through the calculations explicitly. To zeroth order, we simply found no scattering, that if we only looked at that part of our theory, the only thing we'll find theoretically is that we have no scattering. Whatever you put in is what you get out. But once we added another term to make the results more accurate to first order, this is what we found, that there was still no scattering with the highest frequency. But we also saw there were some incidences of scattering noted in our experiment, though every case still satisfied total momentum and energy conservation without exception. And this will always be true even with S2 and above calculations. You'll always see that prediction from our theory, and that's what you see in real life. Interestingly, among scattering cases, there are equal chances of seeing scattering in any spatial direction. In the next lecture, we're going to calculate S2, our second order term, and here we're going to have to learn how to deal with the mathematically difficult time ordering operator T.